This is the 23rd lecture of this course. Recall that in the last 2 lectures we were talking about linear transformations and in particular linear isomorphisms, and then we discussed the rank nullity theorem. So, let us recall what it was. So, though we have proved in generality, namely that if if V and W are linear transformation vector spaces over some f over f, if T is a linear transformation, then we get V mod kernel T is isomorphic to image of T. Okay. In particular, when V and W are V is finite dimensional, then then kernel T will be finite dimensional. Therefore, V mod W. So, this will have dimension of V minus dimension of kernel, which is known as the nullity. So, this the left hand side is it has dimension equal to dimension V minus nullity of T, and the right hand side being isomorphic to this finite dimensional vector space is also finite dimensional, and its dimension is called the rank. So, we as a corollary we deduce that in particular we prove the following: the dimension of V equal to nullity of T plus rank of T provided V is finite dimensional. V is finite dimensional. Okay. So, we will see some corollaries of this. So, so the theorem, as I said, the theorem does not require the assumption that V is finite dimensional. It holds for any two vector spaces V. So, the conclusion is the quotient by the kernel, the space is isomorphic to the image. We usually refer to these as first fundamental theorem of a linear transformation. So, or first isomorphism theorem. So, once we say it is the first, then automatically the natural question that comes that what are the second and maybe possibly more. So, they are also quite easy to see. So, theorem 2, which we will refer as the second isomorphism theorem. So, what is the situation? The situation is very simple, that again we start with a vector space V, and let us say U and so U and W are subspaces of V. We can then talk about U plus W, which is also a subspace V. So, this vector space has both U and W as subspace. Okay. So, it makes sense to talk about the following, that so from U plus okay. So, let us first look at this. So, whenever we have two subspaces, so it is very natural, and when we consider their sum, it is very natural to consider their intersection as well. Okay. Because it is trivial. If it is trivial, then the sum becomes direct. So, what we do now is from U cross, so this U plus V, which is a subspace of V, we can then quotient it out by U. Okay. Now, the question is can we see this space in terms of the intersection, and in fact that is exactly we would like to see. So, what we will do is a very straightforward thing. So, U is a subspace of U plus W. So, from U to U plus W, we consider the usual inclusion map, x b is being mapped to x, okay. X is being mapped to x, and then with that I will consider the quotient U plus W modulo W, okay. So, thus a typical x from here, it goes to x here and then it is being mapped to x plus W. So, it is a linear map, okay. It is a linear map. Now, the question is, so you take the composition, So, it is a linear map from U to U plus W whole mod W. So, what is this space actually? With the vectors of V, with the vectors of U, we have added the vectors of W, and then whatever lies in W, we are equating that to 0. So, the first feeling that we develop hearing that is only the vectors, I mean the vectors which are in U, only those vectors may survive. I mean the vectors which are coming from W, since they are just being mod out to 0, so only the vectors from U can at most survive. Now, it may so happen that the vectors which are both in U and W, they are also killed to 0. So, that means which vectors will survive? The vectors will survive which well, we will see that which are somewhat which, well, let us do it, that is better. So, let us first observe that this composition is onto. Why so? So, if you take a typical coset here, a typical coset looks like U plus W plus W. Now, the way addition in quotient at the level of quotient is here defined. So, this is U plus W, that shows that any coset here is a that admits a pre-image under this diagonal map. So, this is an onto homomorphism onto linear transformation. Now, we have to look at its kernel. What is the kernel? The kernel is if as I said, a typical x is going to x plus w here. So, x plus w is equal to w, it means x is in w, if and only if. So, so therefore, it shows the kernel of this map is precisely u intersection w, right, because the x which are going to w here, though if an x goes to w here, then x has to lie inside w. So, therefore, the first isomorphism theorem guarantees u modulo u intersection v to you have a map, namely the map that we obtain from the kernel to image. So, and this map by this symbol I am saying that this map is we get this map is an isomorphism, right. So, I repeat, from u to u plus w modulo w, we get the map, very natural map, and this is onto linear transformation which has u modulo u intersection w as its kernel. So, then from the first isomorphism theorem, we have an isomorphism between this and that. So, the theorem that we have proved is the following. Then V is a vector space. So, u plus w is u plus w modulo w. This vector space is isomorphic to u modulo u intersection w. Okay. So, if V happens to be finite dimensional, then you can calculate the dimension of both the sides. So, what is the dimension here? Dimension of u plus v, u plus w minus dimension of w, and that you see, and you see here this is dimension of w minus dimension of u intersection w. So, if you bring them on side, you got the dimension formula for the sum of two subspaces. So, basically what you have proved, what we have proved there, this is a generalization of that, okay. Fine. So, this is the second isomorphism theorem. The third, there is a third isomorphism theorem which talks about repetitive quotients. So, this is we called as the second isomorphism theorem. Second isomorphism theorem, and then we talk about the third isomorphism theorem. So, you see the second isomorphism theorem is just is proved, though it is called an isomorphism theorem, but is actually proved using the first isomorphism theorem. We are going to say the same for the third isomorphism theorem as well. So, hence instead of saying it first isomorphism theorem, usually it is also called the fundamental theorem of linear transformation. So, let us come to the third isomorphism theorem. It says as follows, as usual we have a vector space V, and we have a subspace V, and furthermore let us say we have another subspace, we have also a subspace of W. Okay. So, if you use a subspace of W, it is naturally a subspace of V. So, thus we have a vector space, a subspace, and the further subspace of that. Now, what can happen that you can consider quotients in two ways. So, what you can do is you can directly consider V modulo U. So, remember that how do we perceive the set of cosets. So, in V mod, in a coset V mod W, so the elements of W, they are now equated to the 0 vector. Okay. So, we have made the vectors in the subspace, we have made them 0 in a coherent way, which does not mess up the structure of vector space structure of V. So, you can have this quotient, and similarly you have the subspaces. So, what you can do is you can consider the quotient of W by U, and then accordingly you can consider the quotient V mod W. We want to see whether they have any connection between them or not. Okay. So, before that we have to observe something, that under linear transformations there is a correspondence between the subspaces. So, let me first prove that, then I will come to the proof of this. So, there is this more fundamental. So, if V to W is a linear map, and then if then one has the following. First of all, what are these? So, if V prime is a subspace of V, then T V prime will be a subspace of image of T. So, the verification is a routine one, hence I am leaving that to you. Similarly, if W prime is a subspace of W, then T inverse W prime is a subspace of V. Okay. And so, therefore, what we have here, well, so next we should further observe that and try to understand. So, if in particular W prime is a subspace of image of T, then well, or for any subspace W prime here of W, then T inverse V is not only a subspace of V, it is something more. So, further and T inverse contains kernel T. Contains kernel T. Why? Because if you take any vector from kernel T, when you apply T, it goes to 0, which lies inside W prime. So, if you start with a subspace, then its pullback, that is the inverse image, is also a subspace of V containing kernel of T. Okay. Fine. So, and we also notice one more thing, that if W prime is a subspace of W, so we intersect that with image of T, that will be again for that be a subspace of image of T and W as well. So, the inverse image of the intersection is same as the inverse image of W, because that follows more generally. So, what I am saying is that T inverse of W prime intersection image of T is same as T inverse W prime. Okay, that is very easy to see. So, therefore, we can only consider the subspaces which are contained inside the image. Okay, fine. So, thus we have two collections. So, in one hand we have a collection of all subspaces of so we have the collection of all subspaces of image T, and when we take their inverse image we get subspaces of V containing kernel of T. So, therefore, let me write in this way. So, let C1 be the collection of all subspaces containing that contain kernel of T, and let C2 be the collection of all subspaces of image of T, and we have already seen the following, that from C2 to C1 we have a map. What is the map? So, a typical member here, if it is W prime, then that is being mapped to T inverse of W prime. So, let us call this map as phi 1, okay. And on the other hand we have a trivial map, we have a obvious map from C1 to C2. So, let us call it phi 2. So, what is that map? A typical V prime is being mapped to T of V prime. Okay. So, we have two collections. In one hand we have all subspaces of V containing kernel T, on the other hand we have all subspaces of image of T, and we have mechanisms to construct a subspace containing kernel of T from a subspace containing a subspace of image of T, and a mechanism to construct a subspace of image of T starting with a subspace of V containing kernel of T. So, now it is easy to see that it is a set theoretic exercise that both phi 1 and phi 2 are inverse to each other. So, that is a pretty much set theoretic exercise. The third thing is phi 1 and phi 2 are inverse to each other, or in particular the collection of subspaces containing the kernel the collection of subspaces containing the kernel and collection of all subspaces of image, they are in one-to-one correspondence. Okay. As an immediate corollary of this proposition, one has the following, that if V be a vector space and W be a subspace of V, then in view of the quotient map from V to V mod W, which has W as its kernel, we can simply say that what are all the subspaces of V mod W. Remember, this map is an onto linear transformation. So, the subspaces of V mod W are in one-to-one correspondence with the subspaces of V containing the kernel W. So, you can say that the subspaces of V mod W are precisely of this form, namely some V prime modulo W, where V prime is a subspace of V containing kernel of T, such that okay. So, therefore, any subspace of V mod W can be written uniquely as the of the uniquely in the form V mod V prime mod W, where V prime is a subspace containing kernel of T. Okay. Good. So, that gives me the description of very concrete description of all the subspaces of V mod W. Okay. Now, with this let us come back to this third isomorphism theorem. So, what are the situations here? If we remember that V mod W, the V mod U is a vector space, and since W is contained inside here U, so we have W mod U a subspace of V mod U, right? Okay, V mod U, and we have V mod W. So, since this is a subspace of V mod W, V mod U, then we can talk about the quotient, right? W mod U. Okay. So, we can so if we have U a subspace of W which is a subspace of V, then we can directly take the quotient V mod W, or we can have these two quotients and then further a quotient. So, the question is whether these have any connection with or not, and that is actually very easy to that is the main content of the third isomorphism theorem, which we will prove now. So, this is pretty obvious. So, when I am going to rub that, so try to imagine that given a linear transformation. So, subspaces of V are going to the subspaces of the image of T, and subspaces of the image of T are being their pullbacks are subspaces of V containing kernel of T, and in fact these two collections of subspaces are in a bijective correspondence with each other. Okay. So, we will now come to the third isomorphism theorem. So, as we expect that we may expect that there is an isomorphism between them, but we have to construct the isomorphism carefully. So, what we will do is, so from V I would first take the map, I first consider the map to V mod U. So, what is the map? A typical vector V is going to V mod U. Okay. Now, V mod U to, because V mod U has a this as the subspace, right? This as a subspace. So, therefore, so this is the projection to this, this is the projection of V to this, and here also you have a projection. So, therefore, this fellow is being mapped to V mod U plus the subspace W mod U. Okay. So, well, I have not verified yet, but it is obvious that from the definition that if two linear transformations are being composed, then it will also be a linear transformation. In fact, we might have used it earlier. Since it is so obvious that I just used it, I did not even prove. Yeah. So, I did not even realize that I am using anyway. So, here we have a linear transformation from V to V mod W. As expected, we will show that this linear transformation is onto. Why so? That is very easy to see. A typical vector, how will a typical point in this double quotient look like? So, first of all, it has to be of the form some point in V mod U, let us say V plus some point here, a typical point here looks like this, plus W mod U. Okay. You see that this is the, and I mean I try to understand. So, how will a typical point look like? A typical point here which looks like x plus U, where x lies in V and then the subspace, and therefore, you can see that this is the image of the point x in V. So, this is an onto linear transformation. We now have to talk about its kernel. So, once the kernel we know, then we will simply use the fundamental theorem of linear transformation. So, what is the kernel here? So, a V is going to this particular coset here, and here what is the 0 vector in this a repeated quotient. So, the 0 vector will be W modulo u. Okay. So, therefore, if V lies in the kernel, then what might happen is V plus u lies in the vector W modulo u, right. Therefore, V plus u should be, I should be able to write that as W plus u for some W in W. Now, when we say two cosets are equal, if V minus W lies in u, now u lies in W. So, if V minus u, so if V minus W lies in u, then V minus W lies in W as well, and W lies in W already. So, therefore, that forces V to lie inside W exactly. So, therefore, that shows the kernel is W, and hence, so this is my map, this is the linear transformation V going to here is onto linear map. So, therefore, we have a isomorphism from V mod W to this. So, that establishes the isomorphism of the repeated quotient and V mod W. So, yeah, so these are the first these are the isomorphism theorems yeah. So, these are the main three isomorphism theorems which we need to use very frequently, but remember the fundamental one was this. Okay. And one thing again I would like to note, I would like to tell you that it is never assumed that any of this is finite dimensional. Okay. Good. Now, we will come back to the rank nullity theorem and derive some consequences of the rank nullity theorem. So, corollary consequences of rank nullity theorem. Consequence of rank nullity theorem. Okay. So, remember that if x and y are two finite sets and suppose that they have the same number of elements, then a map F from x to y, this map is injective if and only if surjective if and only bijective. Okay. So, we are going to see there the analog of the that phenomenon in the context of finite dimensional vector spaces. Okay. So, as expected that let V and W are finite dimensional vector spaces, over F, and T be a linear transformation from V to W. So, then the following are equivalent. What are the following? So, first of all, suppose, so when we have finite dimensional vector space V and W T, then we have this rank nullity theorem. Okay. So, if T, suppose T is injective, so T is injective if and only if we know that kernel T is trivial, therefore, the dimension is 0. Now, if the dimension is 0, well, I need to assume one more assumption, spaces such that the dimensions are same, then the following are equivalent. So, if the map is injective, then nullity is 0. So, therefore, dimension of V equal to rank of T, that is rank of T is image of T, and since rank of T is less or equal to dimension of W, which is same as dimension of V. So, it follows that the dimension of the image, so the image has to be equal to whole W. I repeat, if the map is injective, then dimension of V is rank of T and dimension of V is same of dimension W. So, rank T is equal to W. What is rank T? Image dimension of image T, and image T is subspace of W, therefore, image T has to be W. Hence, so T is 1 1 or equivalently nullity T is 0, T is onto, equivalently rank T is well, let us dimension W, and then of course, T is an isomorphism. Okay. So, and so we have proved one direction, that is if T is 1 1, that T is onto, and then on the other hand, suppose T is onto. So, that means rank T is dimension W, which is dimension V, then that this formula forces nullity of T to be 0, that means the dimension of kernel is 0. So, the kernel is trivial. So, T is 1 1. So, if we know that between two the two vector spaces having the same dimension, then any linear map between them, if we want to show that linear map is an isomorphism, we do not have to check both the condition, then there is 1 1 and on 2, it suffices to verify 1. So, whichever turns out to be convenient in that particular context, we will do that without any hesitation, because that has given me the complete guarantee that always I am going to get an isomorphism. Okay, so let me give you 1 or 2 examples of this. So, first we will, so in order to talk about this example, we first talk about an important and commonly appearing linear transformation. So, recall that if T is a variable, then what is Ft? Ft is the collection of all polynomials in T. Now, and fix any f in F, then we have a, I would say we have a linear transformation from Ft to F. Namely, what do we do? A typical polynomial Fx is being mapped to f of alpha. Okay. So, this you can easily see, it is a homomorphism, sorry, it is a linear transformation. So, it is a linear, because if you add two polynomials and then evaluate then at the point alpha, that is same as you individually evaluate them at alpha and then add them, and similarly for scalar multiplication. So, we usually call it evaluation alpha. So, this is a linear transformation. Okay. Now, what we will do is something, so using these evaluation maps, we will make some another linear transformation. So, choose, so let's consider m points in F, not necessarily all of them are distinct. So, corresponding to each alpha, I have an evaluation map, evaluation linear map. Okay. Now, what I want to do is, from here f to the power m, I will send a map. What is the map? A typical x will be sent as f of alpha 1, f of alpha n. Okay. You can see exactly in the same way, this is also a linear transformation, right. So, the same kind of argument goes here as well, I mean if you you have to observe that when you add two such tuples, then the addition is happening pointwise. So, if since each and every coordinate go since each and every coordinate, that is sending f x to f alpha I summation, but on the you can do that, but what I am telling you is try to see some something which will motivate you to consider some, which will motivate you to think of a general phenomenon which might happen for try to think of a general phenomenon which is prevailing here. So, what is prevailing here is if you if you just stick to one I, so then f x tends to f alpha I is basically what you are doing is so you are only considering the ith coordinate of this map, and for each I we have seen that map is linear. So, therefore, we are expected that since this coordinate is linear, hence the map happens to be linear, right. So, well, let me say this is the correct time, since we have observed that if each coordinate goes linear, then the map is expected to be linear. In fact, here we have seen it becomes linear. So, it is the time to formulate and prove that in generality. So, what is our setup, that V be a vector space, and let us say u1 up to uk are all vector spaces over K. Remember that u1 up to uk, this Cartesian product it is also a vector space with respect to coordinate wise addition and scalar multiplication. So, basically then suppose we have a map here, and let us denote that for each I. So, ui the following map, that x y u1 up to uk, dropping that to ui. Okay. We have this map, let us call it pi I, right. So, the first observation is each pi I is linear, it is very easy to see, each pi I is linear. So, the first thing is each pi I is linear. Now, if T is linear, then T compose pi I will be linear, because the composition of two linear maps are linear, is linear. So, if T is linear, then for each I T compose pi I is linear. Now, we ask the reverse question, that is, suppose if each T compose pi I is linear, then what happens? So, suppose that each T compose pi I is linear. Then what happens? Can we say T is linear? That is very easy to see. So, what do you need to do to prove T is linear? T of x plus y, we have to see whether that is Tx plus Ty or not. Okay. So, we have to just observe that each Tx, so Tx is nothing but T compose pi 1 x, T compose pi k x, is not so? Because if Tx, let us say it is y1 up to yk, then what is T compose pi I x, T compose pi I x. So, what I am saying is, suppose Tx is y1 up to yk, okay, then what is sorry I have interchanged the order, pi I compose T, pi I compose T, okay, So, then what is pi 1 compose t of x y 1, right. So, similarly what is y 2 pi 2 compose t x. So, t of x is generally this, and if we know that and then it is very easy to see t of x plus y is pi I compose t of x plus y pi 1 pi k compose t of x plus y. Then it is very easy, you can write, since we have assumed all these are linear. So, from that it follows pi 1 compose t of x pi k compose t of x add pi 1 compose t of y pi k compose t y, right, because each of the term is the sum of, so a typical ith term here is the sum of the ith terms of this and that. Okay. So, what does that show? And this is for the addition and same for the scalar multiplication, which I am leaving to you. So, that shows that if each pi compose is linear, then t is linear. So, t is linear if pi I compose t for all k. So, what is the lesson of this general theorem? Suppose from a vector space we have a map to a product of vector spaces, then if so then these we call the coordinate projections, this pi i's. So, and pi I compose t, if we denote this by ti is called, we will say that these are the these are the components or coordinates of ti in this context. So, what it says is that if all the coordinates are linear functions, linear maps, then t is also linear, right. So, that is how I was telling you in this context that we have proved. So, if for each any alpha the map x, if x goes to f of alpha I, so this is the ith coordinate of this map. Since we have seen that the ith coordinate is a linear function, therefore, this will be a linear map. So, I repeat that without getting into all coordinates, you can simply prove it directly using the similar argument that which you have used here, the similar argument, which is an obvious one that shows this is also homomorphic, this is also a linear transformation, but while you prove that, you see that ultimately what you are using is at every coordinate level the linearity of this map. So, that observation motivates you to think of the general theorem. Okay. So, therefore, in view of that, whenever we are supposed to prove the linearity of some map, then we know that it is enough to look at the coordinates. I mean yeah. So, enough to look, or maybe on a coordinate is may not be the better word to use here, because already we have used the word coordinates here. So, let us call these as the projection to the ith component. So, yeah. So, projection. So, this called the projection to the ith component. So, the projection of t on the ith component, that's what you can say here, which means is pi I compose t. Okay. So, therefore, if I am supposed to show this map is linear, I will look at all the projections of I will compose the t with each and every projection pi I. Okay. So, yeah, if in this context you want to say after projecting these are the coordinates, that is fine, but do not confuse that with the with the term coordinates that we have used earlier, but we will indeed show that that is a special case of this, but let us defer that for the time being. here it just means that the composition with all the projections, if these are maps from V to each E y. So, if these are linear, then T will be linear. Okay. And in particular context, so like when the codomain space becomes very huge, but nevertheless it can be considered as the Cartesian product of small subspaces, then composing T with each of these pi i's, that will make our situation simpler in the sense that now the maps are from V to a simpler space E y. So, if I can show them they are equal, then it will be for each I, if we can show that, then we can prove T is linear. So, let us come back to this context. Okay, here. So, this map is linear, either you do it directly or you use it. Now, now as I said, we will derive some we are going to show you some consequences of what I say rank nullity theorem. So, now look at the following, that so this is a map, linear transformation. So, the inside the linear Ft you have the subspace of all polynomials of degree at most n. So, I mean if you want to denote this by Fn, so Fnt denotes the set of collection of all polynomials of direction, all polynomials of all polynomials with degree less or equal to n, and and if you take m equal to just n plus 1 or even higher, okay, and further assume that each alpha I not equal to alpha j. Okay. So, I am considering the same homomorphism restricted to this subspace, and together with some extra condition that m is sufficiently large and no two alpha i's are same. Then this is a linear transformation sending each f x to each I mean f alpha 1, f alpha m. Okay. Fine. So, let us take this better. Yeah. Okay. So, what is the dimension of this subspace? What is the basis for that? 1 up to t to the power n. So, it has dimension n plus 1. Here also you have dimension n plus 1, and we have a linear map. And what about the kernel of this? What about the kernel of this? So, if f x lies in the kernel, that means it has n plus 1 distinct roots, which is not possible unless f is 0. Therefore, the kernel is trivial, and hence as a consequence this is a as a consequence this is an isomorphism. Okay. So, otherwise if it will be much more So, like if I mean suppose you do not use the consequence of rank relative theorem that I have discussed, instead you start with n plus 1 a tuple and try to find out an f such that whose evaluation like this will give you the tuple, and that is somewhat not so obvious. You may need, I mean that is not difficult of either, you may need to do some work, but that is not quite obvious. But in view of this, in view of the consequence, you are now waived from the verification of the surjectivity. Okay. So, a similar example I should also tell you. What is another example I should tell you is another example. So, remember that we discussed so fix and first you fix an epsilon, that is better, and then consider continuous functions for I up to n, and let us look at the differential equation of p1 yn minus 1 and and P n y equal to 0. Okay. So, the solution, so then we have defined that if we take the all continuously nth time continuously differentiable functions satisfying this differential equation, that forms a vector space over R. Okay. Now, what you do is, so V is the vector space there. So, starting from V, we consider a map to R n. So, what is the map? So, any solution here goes to f 0, f prime 0, f n minus 1, 0. Okay. And now you can see that this map is a linear transformation from V to R n, and then using some results from the theory of differential equations, you must have proved that this has a dimension n, and this is it, and also from the uniqueness of solution. So, this map has a trivial kernel. So, I am using results from the theory of differential equations. So, that guarantees the kernel is trivial, and at the same time the dimension of V is n. So, now using the equivalence, we see that this map stands out to be a isomorphism. Okay. Now, we are somewhat yeah. So, let me see whether I have something to say in this regard or not. So, proved that a linear map onto a space of Cartesian products is linear if and only a map is linear if and only if the projections composition of that with the projections all of the compositions are linear. Therefore, as so as a consequence of that, it is also very easy to see as a consequence of this. Suppose I have found a map from V to, let us say, f n. If we regard f n as the n copies of f, so this map is linear if and only if, passing through its coordinate, all the map from V to f, all the coordinates which are mapped from V to f, they are linear, and that is relatively easier to verify. That shows that if we can show that, then we will be able to say whether the original map is linear or not. It seems that I have discussed all the relevant stuff here. So, now let us move on to something else. Fine. Now, what should I do? Okay. So, now we move on to a completely different thing. Let's start with a vector space. Let's start with two vector spaces V and W. Assume they are all finite dimensional, and let T be a linear transformation. So, what we are going to do is we are going to talk about the matrix representation of a linear transformation between two finite dimensional vector spaces with respect to fixed ordered bases. So, these are finite dimensional vector spaces and T is the linear transformation, and we have to fix a base, let us say B1. B1 is an ordered basis of V. Remember, an ordered basis of a vector space is a basis where the elements in the basis are they are arranged in a very particular order. So, let me write this as follows: V1, V2, Vn, okay. And similarly, so this is the basis of V, and then let us call it well, you can just write Bv and Bw. It's very somewhat well, let us write B and B dash because notations will be too complicated. So, and here let B prime be the basis of W. Also I would like to remind you that we made some abuse of notation and agreed that when we say this is an ordered basis, then the order is imposed by the natural indexing, that is, we will regard V 1 is the first vector, V 2 is the second vector, and then similarly V n is the nth vector. And once we have fixed an ordered basis, we have isomorphism from V to f n. What is an isomorphism? We start with a typical vector here. A typical vector here looks like summation x I V I. We map it to okay. So this turns out to be a linear isomorphism. We will say that this linear we will say that given a vector here, so its image under this isomorphism is the this is the coordinate of the vectors with respect to the ordered basis. That is what we have already discussed. Now what we will do is we will now introduce the vectors the matrix representation of this linear transformation. So TV1, this is going to be a vector in. So what is TV1? TV1 is a TV1 is a vector in W. So therefore we would like to write it as a linear combinations of elements of that. So therefore okay, so we will write A11 W1 plus A21 W1 yeah, and then W2 plus A Mn, so A M1 Wm. So similarly TV2, and that is how TV n we would like to write as A1 n W1 plus A2n W2 plus A M n W m. Okay. So corresponding to each I, we have exactly m many coefficients. Okay. So why are we need to look at these? Why are we need to look at these? Because if we know that in order to know a linear transformation, it is enough if we know its the images of a fixed basis, right? Fine. So now we just introduce the matrix of the linear transformation, and then with that I will stop. In the next lecture I will continue with that. So the matrix of the linear transformation T with respect to the basis B1 and B2. So sometimes one use this notation B and B prime. So the ordered basis of the domain space is usually write it on the top, and the other one in the bottom. It is defined to be the matrix of these matrix whose ijth entry is Aij. So let me write it. So first what we will do is we will write down these coefficients along the first column of the matrix A11, A21, similarly AM1. Similarly we look at TV2 and the coefficients which are appearing there. When we split that as a sum of Wi's, then the coefficients we will write them along the second column AM2, okay, and then similarly we go on like this. So in the nth column we will write these coefficients along that. So A1n, A2n, Mn. This is the matrix of this is what we call the matrix of the linear transformation with respect to the ordered basis B and B prime. So in the next lecture I will give you some examples, and we will go on further. So, with that I will finish this lecture. Thank you.